This is our next lecture in Intro to Logic and Troubleshooting. Today we're going to talk about logic gates and Boolean algebra. So here's a quick overview of the discussion that we're going to have today. So we're going to look at basically how binary signals, just one and zero, are used to perform very complex tasks. And they do this basically with a mechanical relay or something that's stationary, a relay that's stationary, and that would be a transistor. So we use these transistors to build logic gates, which control things, inform machines what to do. And they do that basically using this Boolean algebra. So these are all tools that are going to go uh, in our tiny little toolbox. So this is, again, something we need to consider and something that's important for when we're actually building or troubleshooting these type of systems. So first we'll talk about transistors. So transistors, this is just a crash course. So when you have a circuit and you open it, it doesn't allow electricity to flow through. If there's a switch right here, we have a switch. This switch opens, the light turns off. So it breaks the circuit. When I close the circuit and allow electricity flow through, it turns the light on. Well, there's a way you can do this basically with a magnetic field. So here is an example of if I have a little bit of current running through this element right here has a magnetic field that interacts with this relay and closes it and forces the circuit to be shut, and then when it's off, the circuit turns off. So this is a relay or a switch. So this leads us to transistors. So transistors are switches that can be turned on and off without moving parts. So this is the basic of all modern computing. These are amazing. The material changes when you add electricity, and so it allows for, either it to be a conducting material or not. So this is where semiconductors comes from. So the circuits can perform extremely complex tasks. In fact, your iPhone right here has 19 billion transistors. That's insane. There's 19 billion transistors in this phone right here that I, watch YouTube videos on and stuff like that. Like that's 19 billion is wild. All right, so now we're gonna talk about Boolean and binary. So binary refers to the idea that something can either be on or off. It can either be one or zero. So the cup is either empty or the cup is full. There is no in between. It's open, closed, true, false. So it's a one or a zero. And we use this to build more complex things, to basically take that input and then decide using, okay, is it on or off to do something else. And that's where these Boolean gates come in. So this is a Boolean operator. So it has some sort of input. And the input is true, false, on or off, one or zero. And then based on whatever the Boolean operator does, it's a function, it then spits out some output. And so we're going to look at a few different Boolean operators today. So these are two examples. So these are logic gates. So these Boolean operators are also called logic gates. Two separate examples. We have right here, we have the high beams in your car. So the high beams in your car only turn on if you have the high beam turned on. So if you turn the switch to the high beam and you already have your lights on. If you don't have your lights on, if you don't have your normal lights on, then your high beams are not going to come on. So this requires both of those things. It's an and type of logical gate. The next one down here is an or. It's the dome light in your car. So the dome light in your car either turns on if I open the door or if I hit the switch on the top of on the top of the car. Or both. It doesn't matter. I can do either or and or whatever. Just one of those things has to be activated in order for the dome light to go on. This is an example of a or logical gate. Well, now let's just actually get into the nitty-gritty and define what each of these are. So this is the AND gate. So an AND gate, the circuit looks like this. There's two gates in series, and I need both of them to be closed or in contact in order for electricity to flow through this. You'll notice if either one of them is open, it breaks the circuit and does not allow electricity to flow through this. So here's a truth table. These are what we call truth tables. So basically, we look at all the possible inputs for A and B or C and how many ever inputs we have, and then we look at all the possible outputs based on these inputs. So if I have a zero and a zero, meaning both of these are open, then there's no light. If I have one of them closed, so right here, I have B closed, but A is still open, there's no light. I need both of these to be closed, A and B, in order for electricity to flow through here, in order for this light bulb to work. So this is a AND function. And so this is what it looks like. Just, this is typically how it's written. Again, this is the truth table. We look at all the different possibilities for the inputs, and then based on the inputs, they provide some sort of output. But here, it doesn't matter. The only time an AND function gives you an output of one is if all the inputs are one. So they need everything that goes in to be a yes or to be true or to be one in order for the output to be one. If either one of these is zero, then the output is zero. All right, so next OR. So this is an example of an OR function. So I have a light bulb in my house in the hallway that I can turn on downstairs, and I can also turn off or on upstairs. So it's got two separate, light switches. This is an example of an OR circuit. So here I have electricity flowing through here, and if either one of these gates is closed, then electricity can flow and I can get this light bulb lit. So in this case, the only time I have this off is when both of them are off. But if, here I have open, so A would be open, but B is closed, then electricity just flows right through B. If B is closed and A is closed, B is open, then electricity just flows right through A. If they're both closed, then electricity can flow right through both of them and turn the light on. So this just requires one of the inputs, A or B, in order for it to work. And so this is just, again, kind of neatly, the outputs of the function kind of neatly put. So, like I said, either one of these, if it gives you a one, if either one of the inputs is yes or true, then the output of the OR function is true. So in this case, the only time, like I said, the only time the output is zero or false is if both the inputs are zero. Otherwise, A or B works. Doesn't matter which one. I can have both. Great. All right. Next, we'll look at a NOT gate. So this basically just inverts. So this is actually called typically an inverter. So this is like, think about just a button that I push down and basically it turns something off. So in this case, I have, not pushed in, that means the light's on, and pushed in, that means the light's off. So it's something that closes a circuit or it inverts the signal. And so, like I said, this is called an inverter. So how this looks when we write this down is if A is my input, the little symbol for this is a triangle with a little tiny hat, a little circle hat. And then A bar or not A is my output. So this means the opposite of A. So whatever A was, it's the opposite. So in this case, if A is zero, that means the output is one. If A is one, the output is zero. And these things can only have one input. So the not function only can have one input, but you can put them in series with and functions in order to make more, complex gates. So this is just an example of a not and an and for a pressure transducer light. So basically, it indicates the light goes on in a situation where, if I have the pressure, so it says pressure switch open, that means this, goes to zero. This inverts it. This tells me, oh, low pressure. So the light indicates, okay, there's low pressure in the system. But if the pressure switch is closed, meaning there's something mechanical that has enough, basically there's a spring force or something, and it has to have enough pressure to close it, or it's like um, it's probably a mechanical spring, really, is the best way to do it. But you could also have, even just like I guess a few different materials. But basically, this is just like I said, an example of putting these things in an array and using them in more complex things. All right, so the NOR. So this is the NOR gate is an OR, but it's got a little hat on here, and so it makes it not. So neither A nor B, and then it gives me the output. So if A and B are both zero, this outputs one. In any other case, if I have A or B or A and B, this outputs zero. So it has to be neither A nor B. So this is basically a not function for two inputs. And then this is the exclusive or XOR function. So basically, this has inputs A and B, and it exclusively needs one of them. So it turns on only if one of the signals is on. In this case, I have 0, 0, 0 output. I have 0, 1, so B is on, I get 1 as an output. 1, 0, A is on, B is off, I get 1 as an output. But if they're both on, then I get 0 as an output. So I need exclusively one of them. All right, so next we're going to look at combination of logic gates. So the mathematical study of binary number system and logic is called Boolean algebra. So looking at these things and solving them with symbols and kind of math terms is Boolean algebra. And this is what we do in order to basically set up these PLC systems in order to control big components inside of facilities. All right, so this is just a table summarizing the things we've looked at. So we have the and, the or, and the not. So and is multiplication. If I have y, or if I have output is y, and a and b are my inputs, y is equal to a times b. Or is additive. So this is the addition. So y is equal to a plus b if I have an or function. And then finally not, y is equal to a bar. So y is equal to the opposite of whatever I put in. And then you can also illustrate them like in like circuits. So typically, in a big circuit diagram, you're not going to have these big, triangles or little spaceships or anything like that. It's going to be more compact. And so this is how they're written. We have an OR gate, an OR not gate, a and right here just in series, and then an and not. So this is typically how they're represented, like I said, in big electrical schematics. But we're looking at more fundamentally, okay, what's going on. So we're going to stick to these kind of flow chart diagrams. So this is just all the outputs for everything we've looked at. So and is A and B. I get multiplication, A times B. There's also NAND. So this is anything with a hat means it's the opposite. Little tiny circle hat. So this is A times B, the opposite of whatever that ends up being. Or is A plus B. Nor is A plus B, and then the opposite of whatever that ends up being. If that ends up being 0, then the opposite is 1. If that ends up being 1, then the opposite is 0. And then just a simple NOT gate where it just inverts. So like I said, this is our inverter. And this is just an example of a few different ways we can combine them. But first, we're going to actually look at the laws of Boolean logic. So Boolean logic follows a few of the ordinary laws for algebra. So there's the commutative law, where it's A plus B is equal to B plus A. I can switch the order. A times B is equal to B times A. Same thing, I can switch the order. The associative law, where I have A plus B and then I add C, is still equal to A plus B plus C. So, it doesn't matter what order I do the addition, it's still the same. And then the same thing with multiplication. I have A times B times C is equal to A times the quantity B times C. So it doesn't matter where the parentheses are in this multiplication or addition, I do it all the same. And then it's got the distributive law. So A times the quantity B plus C is equal to A times B plus A times C. But then it's got this weird kind of one down here. So it's A plus B times C is equal to A plus B times A plus C. So this is not true for general mathematics. Like if you try to work this out, you won't get a solution that's satisfying. But this does work for Boolean algebra. We'd have to get really deep in the weeds, and we can have this conversation off screen. But yeah, it's there's a kind of heavy mathematical answer that we could really dive into. All right, so let's just look at an example. So in this example, I have an or, I have a not, and then I have an and gate. So I have A and B going into the or. That gives me A plus B. I have C just as an input into this AND gate. And then I have an inverter, D, I get D bar. So everything goes into this AND. The multiplicate or AND is multiplication. So the final output is Y is equal to D bar times C times the quantity of A plus B. So all of this multiplied together. All right, and then we're going to look at this example here. So this is the first example I flashed up when I was like, oh, like, we're going to learn this stuff and it looks kind of like crazy, but it's really not. Let's break it down now. So first, let's identify what each of the logic gates are. So I have one, two, three nots, and then two ands. So then we start to label the intermediate quantities that go into each of these other gates that are downstream from the immediate inputs. So from B, B goes into a NOT gate, I get B bar. C goes into a NOT gate, I get C bar. A goes into this AND gate with B bar, so I get A times B bar. And then that goes into this AND gate with C bar. So the quantity here that's flowing out of this AND and into this NOT is A times B bar times C bar. That goes into a NOT gate, which inverts it. So the final quantity that we get out of this is A bar times B times C. So I get an output of 1 if A is 0, B is 1, and C is 1. All right, so today we looked at Boolean logic and Boolean logic, and this is just we're just scratching the surface here, but this is used to build these really complex logic arrays and all of modern computing. Everything we do that has any sort of computational component, this is how it works. These logic gates are how it works, and so we learned the fundamentals, and we learned a little bit of the math that we have to use in order to build these things. And we can look at things like this and actually, identify what each of these components are. So this system right here, this is built so that he can put in a, or they can put in a binary input here, and it gives me the actual decimal quantity here. So just using, this is not, these are all NOT gates. Here's an OR gate in here. The rest of these look like they're pretty much AND gates or NAND gates. All of these things we've looked at. So we could actually break this down. So if I had to build this by myself from scratch, it would take hours. But looking at this after what we just learned, I could definitely troubleshoot this. I could look and see which components, what everything is. There's nothing in here that we can't identify. And so, this looks complex, but really, we could tear this apart. All right. Thank you very much, and we'll talk to you soon.